NCR Corporation is a leader in omnichannel solutions, turning everyday interactions with businesses into exceptional experiences. With its software, hardware, and portfolio of services, NCR enables nearly 700 million transactions daily across financial, retail, hospitality, travel, telecom, and technology industries. NCR solutions run the everyday transactions that make your life easier. NCR is headquartered in Atlanta, Georgia, with about 30,000 employees and does business in 180 countries.
Great, thank you very much. It's nice to be here with everyone. And why don't we get started? Get my first slide up there. So I'm going to talk about materials, and maybe just a level set. Materials come in three basic classes. You've got metals, ceramics, and polymers. And I'm going to be focused today on polymers. And everyone here is familiar with polymers. You're sitting on polymers right now. You probably got here in different vehicles with polymeric parts, whether it's a car or a bicycle or a bus or maybe even an airplane. Polymers are used everywhere. They're used to keep our teeth straight, from Invisalign and aligners for teeth. It's used to power our microelectronics. They're used to make computer chips. They're used to make stealth aircraft. They're everywhere. And how many people have ever taken apart something? And how many of you failed to put it back together properly? Well, I'm certainly in that category. But it's really fun to tear down, with permission from your parents, tear down different objects. And it's really interesting to look at all the different parts used to assemble different products that we use, from vacuum cleaners to blenders to cars, and lots of different parts in all the different vehicles and everything. And make sure you have permission if you're going to tear down your car from your parents. But it's really interesting to look at all these different parts and all their different intricate shapes and sizes. And you think about the design teams that go ahead and make all these different parts to assemble new designs. And you have to ask yourself the question, how are parts made out of polymers? And it's actually very archaic. It involves making a cavity, usually in metal, and then melting a plastic and injecting that molten plastic into a metal cavity, and then letting the polymer cool down to a solid, and then opening up the cavity and get the part out of the cavity. This is called injection molding. And imagine, if you're a designer, how challenging it is to get to develop your ideas, because you have to wait on first making these cavities. And these cavities can get incredibly expensive, and it slows down lots of different design teams that are designing new cars, new medical devices, all sorts of new products. And what you design has got to be really simple, because you have to get the part out of the cavity. You can't have a complicated design, because you have to be able to open up the cavity to get the part out. And so this is what I call the tyranny of injection molding. It slows everything down. These tools are very expensive. They often take tens of months to get really expensive, really complicated ones, 4 or 5 months to get even simple ones. They're very expensive, and it slows down design teams from every different industry around the world. And imagine if you wanted to make complicated things in a simple way. The object on the right is made out of one part, but it's unmoldable using injection molding. To make that object on the right, you have to actually make the thing on the left. And it's made out of many parts, and it has to be assembled. And it's got to have places for screws. And those screws often have to have, the other side of the screw has to be thicker than it needs to be to accommodate the screw. If you could actually make the thing on the right, you can make it lighter. Maybe if it goes in a car, it could be a more fuel-efficient car. It doesn't require assembly, and it could be more durable as a part. But you can't make the thing on the right with injection molding, because you couldn't get it out of the mold. How would you make something like this? A lattice. A lattice is something that mechanical engineers have been telling everyone how valuable advanced materials can be, where you have amazing properties, but make it really lightweight and high strength. But you can't make something like that because you can't mold something like that. This is where 3D printing comes in. 3D printing gives the ability of making the complex possible. And you don't have to have the constraints of injection molding to make these complicated objects. And there are a number of different techniques, and some of you are probably pretty familiar with these different techniques for doing 3D printing. One involves what's called fused deposition modeling, which is basically like MakerBot. How many people have seen a MakerBot? Which is like a hot melt glue gun over and over again, right? In many ways, 3D printing is a misnomer. I think of 3D printing traditionally practiced as actually 2D printing over and over and over again, right? There's different types of techniques. The one on the right, this is an image of this. This is selective laser sintering. It's spreading a powder. A laser's hitting that powder, and it's going into the table. And with that, you see this block of powder come up, and buried in there somewhere is your part. And it's kind of like cleaning a fish here. And you can see that, and somewhere in there is a part. Now, my number one take-home message for you to see this video is to realize that this is not a scalable technology for making millions or tens of thousands of parts. This is good for prototyping, making a one-off, but you can just see how complicated it is to make a part. 3D printing has mostly been related to prototyping. It's not had the ability to go into manufacturing. And you realize that all the different products that we use daily, they're not made by 3D printing, because 3D printing has pretty much been limited to prototyping because it takes a long time to make a part. And a lot of you have been using 3D printers, and you know how long it takes, and there's a big lineup to get access to the 3D printer. The parts are mechanically weak because they're layer by layer approach, and the materials used have been pretty limited. So 3D printing has not transitioned into manufacturing. Now, we were inspired by this video. Why couldn't a 3D printer look more like this? Terminator 2, T-1000. And you see this puddle accreting underneath as an object is growing. We were really interested as how could we get something like this from Hollywood to actually work? And that's what we focused on as a team. And so we had developed a process we call digital light synthesis or continuous liquid interface production. And we use light and oxygen to grow parts. And now I want to show you the printer. What happens is this platform is going to lower into a shallow puddle of resin that's UV curable. It can solidify with light. And what's going to happen is the light's going to come up from underneath a very special window at the bottom of this puddle. We're going to play a movie in the ultraviolet, and the part is going to glue onto this platform that lowers in, but it doesn't glue to the window. And it's kind of like the Terminator puddle coming in underneath the part as we elevate the part from the top. And we're actually growing these parts. And this kind of looks like the Terminator movie, right? It's just pulling up out of a liquid puddle. And this is how we make parts. We use light and oxygen to grow the parts. And this window is not only transparent to light, like most windows, but it's also highly permeable to oxygen. And so what we're doing is we're going to play a movie from underneath. And this is a two-dimensional projection using just a classic sort of digital light projection system in the ultraviolet, so 385 nanometers. And this is the 2D pattern that we're going to project constantly. But then we're going to glue the part onto the elevator, and by combining a choreography with a z-axis in this two-dimensional projection, this is how we're going to make a three-dimensional object. Now this is an example of the part. This is a 2 millimeter diameter part growing continuously at 200 millimeters an hour. Now most 3D printers, when they print something, they're printing between 1 and 10 millimeter an hour. This is 200 millimeters an hour, and we've done this at 3,000 millimeters an hour. It gets very hot, it almost catches on fire at that point, but that's okay, we can work with that. So this is a 2 millimeter diameter cylinder growing at 200 millimeters an hour. And notice it's coming right off this window. Here's the window, and the light's coming up from underneath, but it's not sticking to the window. What's happening is the light triggers the solidification of the liquid, but we have oxygen coming through the window as well. How many of you can think of a window or a material that's transparent to light that also lets oxygen in? Anyone think about, I bet you some of you are wearing them. A contact lens. Contact lenses let oxygen through and let light through. And so this window is very similar to a contact lens material, okay? And so what's happening is, I'm going to blow it up a little bit for you, is that the oxygen's coming through and it kills the photochemistry right at the window. So it never sticks to the window. So what's happening is liquid's coming in underneath the part, just like the Terminator movie, and the part is rising up out of the puddle. And that's how we're able to achieve this Terminator-like view. We create what we call a dead zone that's created by oxygen. So even though the light's coming through the window right here, this liquid doesn't solidify because oxygen prevents it from happening. And that's a chemical approach that allows us to do what we do. So now we have a printer that operates 25 to 100, maybe even 1,000 times faster than any other 3D printer. Now we need really great materials. Okay, because if it goes fast and it looks great, it does no one any good if it's a brittle plastic, right? So what we developed, a lot of the polymers that you're mostly familiar with are not made with light. So what our team did was take a page out of something you're probably all familiar with. How many people have used epoxy glue? Right? Epoxy glue often comes in two tubes, right? Tube A and tube B. Sometimes they have different colors, you have to mix them. Well, what we did is, now that kind of glue is not UV sensitive. So we developed something we call dual cure. We took an epoxy system or a polyurethane system or a silicone system that would be reactive upon mixing, but we also made it UV curable. Because our printer is printing so fast, we can deal with reactive chemistries and make them UV curable. So what we do is we print the part using light, and then we bake the part to give rise to the properties. And so we call that dual cure, and with that, we can achieve the same kind of material properties that you'd love to have in all of your favorite polymers, from rigid materials to elastic materials to crystal clear materials. All the properties you like to have, we have different liquids. And in fact, we have what we call an app store for resins. Just like all the different app stores on your phone, you can go onto our printers, and we have basically you can click on all the different resins and use those different resins to give rise to different properties for your favorite applications. So now we're at the point of where we talk about stop prototyping, start producing, because the printer's going really, really fast. We have the properties of the final parts that you need in a real application, and we can now start thinking about actually mass production. In fact, can we go back one slide? And these are our printers lined up in a mini factory. And this is an example of 10 of our printers lined up, and this will make over 1 million electrical connectors a year, and parts that are really small, and we can make lots of them in the millions of pieces. And so we're working with this type of technology in a wide range of different industries, including consumer, major industrial, and medical, and I just want to show you some of these examples. And the first one I'm going to show you is one from our great partner and customer, Adidas. I'm going to play this video.
When we first started with the idea of Futurecraft, it was to sort of guide us, to set us on a path.
It's a mindset and it's a philosophy to try things.
We're always bringing in new influences, new ideas, new collaborations. 3D printing, for example, was one of these new technologies that really had unlimited possibilities. You know, the initial problem was, okay, can we actually make a running shoe out of 3D printed material that really works and works well?
So when we started thinking about doing 3D printing, we wanted to use liquids, because liquids give you the most flexibility in material design. I think of light as a chisel. Light triggers the solidification of the liquid, but oxygen inhibits it. That allows us to have the object grow.
What's really interesting about this collaboration with carbon is we're seeing a convergence of a completely new manufacturing technology.
We're going to scale it with the best industrial partner in the business.
We're able to deliver tens of thousands and move into hundreds of thousands and into the tens of millions. You know, that's clear in front of us.
We have this amazing opportunity to innovate the printing process, the liquid rising.
And growing in that context can give you new design thoughts you've never had before and new performance capabilities that wouldn't be possible by traditional manufacturing.
This three-dimensional mesh structure, it's a lattice, it's a matrix, it's a web of individual elements. Each one of those little elements is tuned specifically for a purpose.
These lattice structures behave quite differently than anything we've dealt with before. They're much different than foams. Now we have every individual area of the shoe to work with, which is a completely new horizon for us and a new venture.
If you really want to make a shoe that's a size 9, that same shoe for someone who's 180 pounds versus 100 pounds has got to be different.
We can go in within every single cell and engineer that exact cell to do exactly what the consumer needs it to do just for them.
That's fascinating. That's going to change how we create products and certainly how consumers experience products. And I think that's how we see something like Futurecraft 4D playing into the life of an athlete. I would say this is just the very beginning, and that sounds silly and cliche, but who knows, man? I don't know what's next, and that's what's great about going to work every day.
A little bit of a Westworld ending here. So we're very excited about this application. Adidas makes 420 million pairs of shoes a year. 420. And roughly 50 of our printers will make 1 million pair a year. And so we're very excited. We're going to make over 100,000 this year, and we'll be making millions of pairs going forward. So it's very exciting. And the 4D, you saw that young lady running, and then she hit that force plate and the high-speed videography. That's the data capture. The 4D stands for the 3D lattice, and the fourth dimension is you. It's your data, it's your biometrics, it's your gait, it's how you run, and that's how we make these amazing shoes. And so these are all the different designers are coming through, and it's fun to work with the different designers with Adidas and the Y3s and Kanye's getting involved and all these different running shoes, so it's fun. This is a new basketball shoe with these side vents. It's very exciting. It's fun being a chemistry professor wearing, being the cool kid on the block, having some of the best sneakers. But what we're doing is we're using advanced computer-based modeling, finite element analysis, and cloud-based computing to calculate the kind of deformation that's personalized for individuals. And so you can basically collect the data. We have a library of matrices with different unit cells, different strut thickness, different materials. And we can give rise to different mechanical properties, and we can do all this in the cloud using cloud-based computing, so we can take your data and make a shoe that's customized for you. It's a really exciting future. And this is just the beginning, that there's lots of different applications in the consumer products industry where you have different materials from running shoes. Think about high-speed VR, AR headsets, equipment that protects helmets and protects your head from collisions or concussions. I didn't appreciate the physics of applying mascara. Mascara brushes are absolutely amazing products for doing that, and we can make some really amazing products using 3D printing. Think about the automobile industry. Everybody's trying to make new cars, and cars that are autopilot cars. Think about all the different design teams that have to make new brackets and new sensors. And it's interesting, you want to make cars that are more fuel efficient. You can put a matrix, instead of a solid part, you can put a lattice inside these parts, and now you can reduce the mass by 44 weight%. So if you're trying to make cars that are more fuel efficient, right, you can start doing that with lattices. And it's something you couldn't do before. And then you think about, so this is a little hard to read, but this is all about autonomous vehicles. Today, people drive cars, and in the future, the car's going to drive itself. In order for that to happen, you have to dramatically increase the number of sensors in a car. You go from 8 sensors to, and you increase that by a factor of 8, right? Well over 60 sensors needed to drive a car. Every one of those sensors needs a bracket, and they're all different. And you think about how much faster the development of autopilot cars will go if you didn't have to wait for an injection molding tool. You go from 2 miles of wire in a car to 12 miles of wire when you have an autopiloted car. All these things are really hindered if you don't have an ability to make parts quickly. So these are all different kinds of parts that we're making. This is a seat using an elastomer lattice. That's very exciting. And probably one of the areas that we're very excited about is medical products. And the idea that we can make all sorts of advanced products for people, including digital dentistry, right? In order to keep your teeth straight, or denture bases and denture teeth. These are all different materials made on our printer with very high resolution and accuracy. And the idea of going back and getting an impression is over. Everybody's teeth are now getting scanned digitally instead of the old way with impressions. It's a very exciting future. We have companies developing entire new products based entirely on 3D printing. And this is a company here that spun out of my academic lab that's delivering drugs locally to tumors for pancreatic cancer. So just think about the impact of helping from cars to running shoes to new medical devices, all because you can make products, really complicated products, more easily using a digital fabrication technique. And maybe back to where we started, certainly one of the fun places for us is to be powering Hollywood. And I thought I'd just show these kinds of equipment from some of your favorite stars, and I wanted to play this last video here. Yeah, so it's really fun making all these products, and this is one of our favorite customers. These are the Alien King models that they make, and every one of these parts is made individually on our printer, and they're pulled right out of the liquid. They have some supports on them when they come out, and you can make some really complicated structures. And so you can just let your imagination run wild with incredible detail. And so what's really cool is you can now start making lots of these different products and do with all these different designs with exquisite detail. Things you could imagine if you had to make an injection molding tool for every one of these parts. It would be virtually impossible to do that. And so this is a whole new world, being able to make exactly what you want, but to do it not just for prototyping, but for scale and manufacturing. And the idea that you can have, once you have a digital fabrication technique, you can use this in a whole host of different industry verticals. Now, what this is all about is a team of amazing people from a lot of different disciplines, hardware engineering, software engineering, and molecular science, with a lot of different backgrounds coming together to try to do the impossible. And it's a real exciting time for us. And we believe strongly that light as a chisel will be an amazing frontier to make complicated things that you cannot make by injection molding. Thanks for your attention. Happy to answer any questions.